So I'd like to introduce the next speaker, Hossain Chizari. Hossain has always been fascinated by science and engineering, and for the past 17 years has dedicated his career to method development and computational fluid dynamics. Hossain works with Kindeva drug delivery, and in his role, he is working to expand the knowledge of modeling and simulation in this industry. He holds degrees in both mechanical and aerospace engineering. Welcome, Hossain.
Thank you very much. Okay, hello everyone. Thank you very much for being here. First, I want to thank the DDL committee for organizing this and giving me the opportunity to present our work. So today I'm going to share with you our new numerical framework that we developed to predict Low-GWP pMDI spray characteristics and drug deposition from the first principle. So a little bit of a background. So pMDIs are popular. They're widely prescribed to treat asthma and COPD. And they are portable, they're lightweight, and they are useful. But there are some challenges, one of which would be they're using the high GWP propellants. And there is a global consensus to phase down and eventually phase out these high GWP propellants. And now the industry is responding by considering to reformulate to low GWP propellants. So what is the motivation? So despite the fact that pMDI is actually a long presence in the market, our fundamental understanding of it is very primitive. We don't know too much about high-speed multiphase flow or atomization in the fundamental level. And now we want to change the propellant, so it makes things even worse. And then there are only a few fundamental studies out there, which is either semi-empirical or very limited in the aspect, in a theoretical way. So we believe that there is a gap of a comprehensive first principle approach. And then that framework is going to reduce the development time, cost, and also the risk. So what is the aim of this study? The aim is to fill the gap. We want to develop that first principle. And then how we're going to do it, we're going to use multiple layers of mathematics, first principle physics, and also numerical methods to do that. So let's see how the model works. So as of every other model, it has some inputs, material properties, the geometries of the valve and actuator, environmental condition, and so on. All these inputs are going to go to the model, and the model itself contains three main steps: internal flow, atomization, and CFD. So the internal flow is going to calculate the flow characteristics, such as pressure and temperature, and then we use those values outputted from internal flow and put to the atomization model to get the near orifice droplet size distribution. So combining these two outputs, we're going to put it into the CFD model as a spray source, and then we're going to find out how the spray dynamics would be and what would be the drug deposition. Just note that for this study, we're using suspension salbutamol in HFA152A. So a bit more context here. So we're using RefRob 10 for all the transport and thermodynamic properties. Our internal flow model is based on the previous one developed by Gaftosh and colleagues. And also the atomization model is based on Ritz instability equation. So we have a separate poster for this, so please do check it. For the CFD model, we're using a generic pMDI and a USB port, and we discretize this by around 10 million elements. And then the air is going to come in at 30 liters per minute in, and the outflow at atmospheric pressure. So the spray part is going to come from the internal flow model, the gas part, and the droplets coming from the atomization model. So that's how we can construct the spray orifice. So just note that the droplet composition would be the suspended salbutamol particles in the HFA152A. We use different aspects of the physics. We use large eddy simulation for turbulence, and we use two-way coupling and evaporation and condensation for the droplets. So now I'm going to talk about some results. Just before I go through this, just note that we wanted to make sure the model is working, not just the end result. We check the steps in between to make sure everything is actually tied up. So this is the internal flow model validation. So as you can see, the results are pretty much following the experiment very well. There are some differences due to simplifications in the model, but the trends are good, the maximums are okay, And you might ask, why expansion chamber comparison for temperature and pressure? The reason is that expansion chamber is right before the atomization, and we have to get this right to make sure the atomization model is going to work. So in the next one, what you see is the atomization results. So we have a droplet size distribution. We have experimental data for HFA134a, which is compared to the atomization model predictions. The comparison is fairly well. And then this gives us confidence that, OK, so the model is going to work. So we take the model, and then we use it for HFA152a. And then we're going to put that HFA152a results in our CFD simulation. Just know that we don't have experimental measurements for HFA152a yet. So now I'm going to show you the CFD results. So in the top view, what you see the side section of the near orifice region. The bottom one is, I should have a pointer here. Yeah. So the bottom one is the top view. This one is the top view of the near orifice. And then what you see down here is the actuation time. And then note that this is a slow motion. So we're going to slow it like 100 times slower than what actually happened, just to make sure every little detail we can actually follow through. So let's have a look. Yeah. So as you can see, it is very chaotic near orifice, and it is three-dimensional. And then while it is playing, you can see that the plume here is actually going left and right. And then here is a little bit upward, which is because of the whole co-flow coming down and going up a little bit. So it's a momentum transfer between the two. And then there is a huge deceleration, 50 plus meters per second to around 10 in perhaps 20 millimeters or so. So it looks OK, it looks nice, but we want to check everything. So we check also vorticity. So vorticity, in effect, is like a turbulence measure. So whenever you have a high vorticity, you will have like a turbulence intensity. And then also it's a parameter you can check if there is a mixing there. So if it mixes a lot, it means vorticity is high. So let's have a look. So you see in this near orifice region, you see a very high vorticity rate, which is expected. The jet velocity, 50 plus meters per second, compared to the whole 30 liters per minute, 5 or 6 meters per second. So the vorticity here is high. It's going to eject all these droplets in, and then some of them are going to deposit, some of them are going to escape. While this is playing, interesting parts are actually some of these areas here that we have recirculation. You can see in these four, we will have some recirculation there, which is very interesting. And then, again, it is very chaotic, and it is three-dimensional. As the time goes around 0.18 seconds, the spray is going to be finished, the actuation is going to be finished, and then the co-flow is going to take over and eventually push these droplets down and then to the escape. And some of them are going to deposit again. So this is a very beautiful view of the whole thing, but the point is that why we are doing this. I mean, we need numbers to help developments. This is only a view. It's only like a beautiful picture of it. So this is the juicy part for the developments. So on the left, what you see is the drug mass or segmented drug mass for injection for the USP-IP and for the escape. You see two size distributions here for the injected or ejected and also the escape. And what you see here is like a 2D histogram, which shows where and how much drug is going to be deposited within the USP. So let's have a look. So while it is playing, you see the ejected goes up. Immediately after that, deposition starts. With a little bit of lag, escaped particles are going to go out of the domain. And then this is the distribution of the droplets, which actually has the drug. And this is the distribution that is escaped. And you can see it is shifted to the left. Expected again, because we know there's evaporation going on. And this is some sort of like a two-dimensional map that will show where the drug is going to be deposited within the USP in this case. So we did this whole thing for two cases. one for suspension salbutamol, and the other one for solution case, 8% ethanol. And we get good agreement for both, and we're looking to do more of these. So to sum up, I actually introduced a multi-physics theoretical framework to predict low-GWP pMDI spray characteristic, drug deposition, and we try to verify the internal flow model, atomization model, and also the CFD model. And then what we're hoping to get out of it is the reduction in timelines through the reduced design iterations and the reducing product development cost and risk. So what would be the next step? First of all, model tuning and validation. That's very important. We want to make sure that this model is actually trustable. We are only scratching the surface. So there's a lot of things we don't know. It's very encouraging, but we have to test. So that's the first part. The second part, we want to go for physics-informed neural network to combine the neural network and the first principle so we can get more, we can get more reliable and faster results. And I want to take a moment to thank all my colleagues. I could not have done this project without the help and support of these very nice people. Thank you very much.